Have you ever wondered why a rainbow appears after the rain? Or why light passing through a prism breaks into different colors? Today, we'll explore a fascinating phenomenon called dispersion, the process that reveals the hidden colors within light itself. And of course, with our learning outcomes, first, explain the cause of dispersion in the prism. Second, describe the effects of dispersion in producing rainbows. And lastly, understand the misconception of light dispersion.
Good morning, everyone. First, I have a question. As you know that we've all seen a rainbow. As you see a rainbow, have you enjoyed the spectacle of rainbow, which is its glimmer against a dark storm sky? How the sunlight falling in clear drops of rain, which it gets broken into the rainbow of the colors we see. The same process causes white light to be broken into colors by a clear glass prism or a diamond. As we know that a rainbow has 6 colors. It has a red, an orange, a green, a blue, and a violet, but sometimes it is indigo. These colors are associated with different wavelengths of light, which it is shown in the picture. With our eye receives pure wavelength light, we tend to see only one of the 6 colors, depending on the wavelength. The thousands of other hues we can sense in other situations, our eyes responds to its various mixture of wavelengths, like white lights in particular in a fairly uniform mixture of all wavelengths. Sunlight, it is considered to be white. Actually, it appears to be a bit of yellow. It is due, or it is because of its mixture of the wavelengths, but it does not contain all the visible wavelengths we see. The sequence of colors in rainbow is the same sequence as the color shown in the picture. This implies that white light is spread out in a rainbow according to wavelength. Here comes dispersion. Dispersion are defined as the spreading of white light into its full spectrum of wavelengths. More technically, dispersion occurs whenever there's a propagation of light or there's a spreading of light, which it depends on its wavelength. Any type of wave can exhibit dispersion. For example, the sound waves, all types of electromagnetic waves, or even water waves can be dispersed according to wavelength. Dispersion may require special circumstances which can result in spectacular displays such as a production of a rainbow. This is also true for sound, since all frequencies ordinarily travel at the same speed. But if you listen to sound through a long tube such as vacuum cleaner hose, you can easily hear it disperse by interaction with the tube. Dispersion, in fact, has a great deal about what the wave was encountered that being dispersed to its wavelengths. The dispersion of electromagnetic radiation from our outer space, for example, has revealed much about what exists between the stars, which is so-called interstellar medium. Again, dispersion is defined as the spreading of light into its full spectrum of wavelengths, which only occurs when there's a propagation of light depends on its wavelength.
Now, before we answer the question, why does dispersion occur, let us first begin with a little imagination. Picture this, a single beam of white light, plain, ordinary, almost boring, enters a glass prism. But suddenly, boom, it explodes into a beautiful rainbow, scattering colors everywhere. Now, the big question is, why does that happen? The secret lies in one word, refraction. Every time light passes from one medium to another, say from air into glass, it bends. But here's the twist. Not all colors bend the same way. It's like each color has its own personality. Red says, I'll take it easy, and it bends just a little. And violet, on the other hand, is dramatic, like I'm going all in, and bends much more sharply. That difference in bending is what we call dispersion. The grand separation of white light into its colorful components. And it happens because the speed of light changes depending on the material it passes through and on its color. You see, glass doesn't treat all wavelengths equally. It slows down violet light slightly more than red light, so as they exit the prism, they part ways, creating the gorgeous fan of colors you see. Next time you see a rainbow, remember, it's not magic. It's physics, nature's way of showing off refraction with a splash of color.
Good day, everyone. Today, I'll be discussing the connection of light refraction to Snell's law, which is also known as the law of refraction. Refraction happens when light passes from one medium to another, for example, from air to water, and it bends because its speed changes. Snell's law gives us the exact relationship between the angle of incidence, which is the angle of the incoming ray, and the angle of refraction, which is the angle of the bent ray. The law is written as n1 sine theta 1 equals n2 sine theta 2. Here, n1 and n2 are the refractive indices of the two media. Theta 1 is the angle of incidence, and theta 2 is the angle of refraction. This means that how much the light bends depends on the properties of the two materials. For example, light slows down when entering water from air, which causes the light ray to bend toward the normal. And now, we will proceed on how to apply the connection of light refraction to Snell's law or the law of refraction. As you can see in the photo, a beam of white light goes from air into flint glass at an incidence angle of 43.2 degree. What is the angle between the red 660 nm and violet 410 nm parts of the refracted light? So the values for the indices of refraction for flint glass at various wavelengths are listed in photo. Use these values to calculate the angle of refraction for each color and then take the difference to find the dispersion angle. So the solution, applying the law of refraction for the red part of the beam, n air sine theta air equals n red sine theta red. We can solve for the angle of refraction as theta sub red equals sine inverse of the refractive index of air multiplied by sine of the angle of incidence in air divided by the refractive index of red in glass. Substituting the values, sine inverse of 1.000 times sine 43.2 degrees all over 1.512. This gives 27.0 degrees. Similarly, the angle of incidence for the violet part of the beam is theta sub violet equals sine inverse of n sub air times sine theta sub air divided by n sub violet. That is equal to sine inverse of 1.000 times sine of 43.2 degrees divided by 1.530, which equals 26.4 degrees. So the difference between these two angles is theta sub red minus theta sub violet equals 27.0 degrees minus 26.4 degrees, which equals 0.6 degrees. So the significance, although 0.6 degrees may seem like a negligibly small angle, if this beam is allowed to propagate along enough distance, the dispersion of colors become quite noticeable.
So good day everyone. So now let's discuss the history of dispersion. So the study of dispersion began in the 17th century with Sir Isaac Newton. In 1666, Newton conducted his famous prism experiment where he allowed a narrow beam of sunlight to pass through a glass prism. So to his amazement, the white light spread out into a band of colors: red, orange, yellow, green, blue, indigo, and violet, forming what we now call the visible spectrum. So before Newton, many believed that the prism itself added color to the light. However, Newton's experiment proved that white light is actually a mixture of many colors that bend differently when passing through a prism, so depending on their wavelength. So later, in the 19th century, another scientist named Joseph von Fraunhofer discovered dark lines in the solar spectrum, which are now known as the Fraunhofer lines. So these lines revealed that each element absorbs light at specific wavelengths, leading to the development of spectroscopy. So this is a scientific method used to identify composition of stars and chemical substances. So in fact, modern astronomy still relies on dispersion and spectroscopy to analyze the elements that make up distant celestial bodies. So now let's discuss the visible spectrum. So the visible spectrum is the portion of the electromagnetic spectrum that the human eye can detect. So it lies between 380 nanometers for violet light and 700 nanometers for red light. So beyond the visible range are other types of electromagnetic waves such as ultraviolet, X-rays, and gamma rays on the shorter wavelength side, and infrared, microwaves, and radio waves on the longer wavelength side. The frequency of visible light ranges from approximately 400 to 750 terahertz, meaning that these waves oscillate hundreds of trillions of times every second. Violet light has the shortest wavelength, as you can see, and it has the highest energy, while red light has the longest wavelength and lowest energy. That is why red light travels farther through fog and is used for warning lights and night vision, as it is less glaring to human eyes. So the visible spectrum is composed of 6 major colors, each with its own characteristics and wavelength range. So violet light, with wavelengths between 380 to 450 nanometers, has the shortest wavelength and the highest frequency. Blue light, on the other hand, ranges from 450 to 495 nanometers and plays a role in the blue color of the sky due to Rayleigh scattering. So where shorter wavelengths scatter more in the atmosphere. Green light has a 495 to 570 nanometers and occupies the middle of the spectrum and is the color most visible and comfortable to the human eye. Yellow light is 570 to 590 nanometers and is associated with warmth and sunlight, while orange light has 590 to 620 nanometers, which is the bridges between yellow and red. And finally, red light, which has 620 to 700 nanometer, has the longest wavelength and lowest frequency. So interestingly, no, our eyes are most sensitive to green light, which is why the traffic signals and night vision screens often use green for visibility. So these colors together form the foundation of the rainbow that we see after a rain shower. So in summary, the phenomenon of dispersion shows us that white light is composed of many colors that spread out based on wavelength when refracted. So this concept was first explored by Isaac Newton and expanded by scientists like Fraunhofer that paved way for spectroscopy and modern optical technologies. So the visible spectrum, ranging from 380 to 700 nanometer, allows us to perceive the world in color, and each hue carries unique energy and frequency properties. So dispersion helps us connect natural beauty with scientific understanding, from the rainbow across the sky to the light pulses transmitting information across the globe. So it is a reminder that light is something that we often take for granted and is full of mystery and scientific elegance.
Now, let's talk about the behavior of colors, specifically red and violet. So, red and violet represents the opposite end of a visible spectrum. Let's first have red. Red has a wavelength of around 700 nanometers and is considered to be the longest among visible colors. So, because of this, it bends the least when passing through a prism or a water droplet. So, this minimal bending means that red light travels a straighter path and appears at the top of a rainbow or spectrum. So, in materials like glass or water, red light travels faster than other colors because longer wavelengths are less affected by the medium's refractive index. So violet, on the other hand, sits at the opposite end of the spectrum with a much shorter wavelength, which is around 400 nanometers. So shorter wavelengths are more susceptible to refraction. So that is why violet light bends significantly more than red when entering a new medium. So this strong bending causes violet to separate more distinctly from the rest of the colors, making it appear at the bottom of a rainbow or spectrum. So, violet light also travels slower in a medium compared to red light because of its shorter wavelength. So, this difference in bending behavior is what gives rise to dispersion. So, examples, first let's have rainbows. So, when sunlight enters a water droplet in the atmosphere, it refracts, and then it reflects inside the droplet, and then it refracts again as it exits. So, each color bends at a slightly different angle, with a red light bending the least and violet the most, thus creating a full arc of colors in the sky. Next is prism experiments. So, prism experiments offers a controlled way to observe this effect. When white light passes through a glass or acrylic prism, it spreads into a spectrum due to the varying refraction angles of each color. So, red light exits the prism at a shallower angle, while violet bends more steeply, forming a vivid display of colors. Next is CDs and DVDs. So, they have finely grooved surfaces that diffract light, producing rainbow-like patterns when viewed under direct light. Next is soap bubbles. Soap bubbles create colorful swirls because their thin films causes light waves to interfere and disperse. Next is diamonds. Diamonds are especially brilliant because the crystal structure has a high dispersion index, splitting light into intense flashes of colors. Last is oil slicks. So even oil slicks on water can produce rainbow effects. So the thin layer of oil refracts and interferes with light, creating shimmering, multicolored patterns. So all these examples show how the physics of light, particularly the behavior of red and violet wavelets, translates into the stunning visual phenomena we encounter in nature and everyday life.
Now that we know why dispersion happens, let's see where this phenomenon sneaks into our everyday world. And spoiler alert, it's everywhere, from the sparkle of a diamond to the fiber lines that power your Wi-Fi. Now let's start with spectroscopy, and I believe it has already been discussed earlier. So this is the science of light detectives. Imagine we shine light from an unknown gas into a prism. The prism splits it, and voila, we get a pattern of colors and lines, like a barcode of light. Scientists can read the barcode to tell what the gas is made of. That's how astronomers know what stars are burning billions of kilometers away. The colors literally tell the story of the universe, and there are other more applications with spectroscopy, especially in medicine. Okay, so next we have optical instruments. Cameras, microscopes, telescopes. These rely on lenses, but dispersion can mess with them. Have you ever taken a photo and seen weird purple or green fringes on the edges? So that's light colors not focusing together because of dispersion. So engineers fix this by combining different kinds of glass to balance the colors back into a single crisp image. So yes, your phone's smart lens correction is really a fight against dispersion. Now, We have fiber optics, where science meets speed. In those long glass threads that carry your internet, dispersion can be a problem. Why? Because the light pulses that carry your data bits of 1 and 0 start to spread out over distance. Imagine if all your words in a message arrives lightly scrambled. That's what engineers prevent by using special fibers that minimize dispersion, keeping your TikToks from buffering mid-video. And finally, gem cutting. Have you ever stared at the diamond under the light and seen those little flashes of rainbow fire? So that's dispersion working in your favor. So gem cutters design sets those tiny polished surfaces at specific angles to maximize how much line bends and splits inside the gem. To the result, the hypnotic sparkle that makes people fall in love or spend too much money. So in short, dispersion can be a scientist's tool, an engineer's challenge, or an artist's secret weapon. So it gives us rainbows, reveals the compositions of stars, sharpens our vision devices, powers our communication, and makes gems shimmer like captured light. So pretty amazing how one tiny quirk of physics, just like changing speed, can color our world, don't you think?
Dispersion misconception. Misconception: white light is made of only one color and the prism adds colors. Correction: white light is actually a combination of many colors. A prism only separates the colors which are already present. It does not create them. Misconception: all colors of light refract at the same angle. Correction: different colors or wavelengths of light bend by different amounts. Violet bends the most, and red bends the least because violet is a shorter wavelength and is refracted more strongly. Misconception about rainbows: rainbows forms because sunlight passes through the raindrops just once. Correction: a rainbow is formed due to a combination of refraction, dispersion, and reflection inside the water droplets, not just one refraction. Misconception: dispersion and refraction are the same. Correction: refraction is the bending of light when it passes from one medium to another, while dispersion is the separation of white light into its component color due to its difference in refraction for each wavelength.
As a summary, dispersion is the process of dividing white light into its different colors. So this helps us understand how natural phenomena like rainbows and the various colors we see around us are formed. So beyond nature, these same principles are also applied in modern technology. For example, in fiber optics, spectroscopy, and other optical instruments. So by studying dispersion and clearing up misconceptions about it, we gain a deeper understanding of how light behaves. So in the end, appreciating how light and color work doesn't just satisfy our curiosity. It also plays an important role in the advancement of both science and our everyday lives.